Okay, AP Calculus BC, Unit 2, Day 3, Continuity. These notes may have been on the back of your Day 2 notes. Some brief notes. There are different kinds of discontinuities where a graph is not continuous. So in this instance, that's a hole in the graph. And what happens is that the graph actually behaves like this parabola, even though it was a rational function to start with. And you could say, okay, well, its zeros are at 2, and then you go up 1 over 1, up 2 over 4. It's just a quick graph. I'm going to graph it lightly. Now, what happens is it looks like this graph, but there is a hole at x equals 3. And then the graph really just looks like this parabola the rest of the time. So this is a hole at x equals 3. We call this a point discontinuity. And we also call it a removable discontinuity. The reason it's removable, and on your homework today, you're going to have some questions that ask you if it is or isn't and how to fix it. It's removable because we can fix it. We can plug the hole. We can just assign F3 equals 1. And now it's plugged. But even easier than that, we could just redefine it as f of x equals the parabola. So this would be, we removed the discontinuity. So that's what they call it, a removable discontinuity. Here's a piecewise graph. We could start with the parabola, up 1 over 1, up, or over 2, up 4. I'm going to just graph it lightly. And then the line, the other part, is -1, has a slope of down 1 over 1, or up 1, left 1, up 1, left 1, up 1, left 1. So that's the line. Now, after I've done it lightly, I'm going to say, okay, well, at 1, to the right of 1 is the parabola, and including 1. So it's a solid dot there because of the or equals to. And I darken that in, put an arrow there. At 1, but not including 1, we have an open dot, and then it follows the line for the rest of the graph. So a lot of times on piecewise graphs, we get these kind of like big things. We call them jump discontinuities. So there's a jump at x equals 1. It is not removable. You can't just connect those pieces and make it like as if it was never there. So it's not removable. And also the limit on both sides do not agree with each other. So limit doesn't exist at a jump. Limit exists at a hole, but not at a jump. So the next one is a rational function, and it has a vertical asymptote at x equals 2. So we draw that in. And then horizontal asymptote, y equals 0 is you go to infinity, goes to 0. Now, on either side, if you're plug 3 in here, it'd be 1. If you're plug 2 in here, or 4 in here, it'd be 1/4. If you're to plug in like, I don't know, 2.5, it would be, I think 4. So something like that. Now on the other side, you're actually getting the exact same values because it's being squared. So this is kind of like that bounce idea on line checks, that it doesn't change sign on either side, even though it usually does. So let's go into towards that. Let's go towards that. So I'm going to go and finish the graph of this. Okay, so that's what the graph looks like now. This there's a discontinuity. You can't draw it from one section to the other without lifting your pencil. We call this an infinite discontinuity at x equals 2. Also, you might refer to as a vertical asymptote. So sometimes we have a couple different names for these. It is definitely not removable, right? You can't just connect the two sides with just plugging a point in or something. So those are three different kinds of discontinuities. Now, the definition of a continuous graph of continuity is that this is just sort of our basic idea of a limit, right? You approach both sides, and they both agree, and they approach the value that would be there. Now, f of x is continuous, so this is the definition of continuity. So a graph is continuous at a point. It can be continuous at a lot of points and not continuous at others, but it's continuous at a point x equals a if the limit as x approaches a of f of x, which would equal some value, equals the actual value of the graph. So the limiting value equals the actual value. Because if there's a hole there, the limit would still exist, but it wouldn't agree with the value of the function there. So if they agree, then the graph must be continuous. Differentiability is a slope issue. Okay. Differentiability means the derivative exists. For the derivative to exist, the slopes have to agree on both sides. And so an example of a graph that, so any kind of corner or cusp or something like that is not going to be differentiable because the slopes don't agree. So I'm going to show you guys. So you could have, the limit could exist and the graph could be continuous, at this point, A. And so it is continuous because the limit as x approaches a of f of x equals the actual value of the function of a. So it's a continuous graph, but like the slopes on the side, a lot of times cusps come in at vertical tangents. And so like the slope here is going toward positive infinity. You might, oh, that's negative. No, that's a positive slope. And the slope here is going towards negative infinity. And even if they're both positive infinity, that doesn't mean they agree, because infinity is its own issue of not being differentiable, but it is not differentiable. So graphs can be continuous but not differentiable. To be differentiable, though, they must be continuous first. So here's some examples like you might find in your home. Find f of x if we remove the discontinuity, which must mean that it's a hole, right? So let's try and see if we can find the hole. This is the difference of cubes. So that's that whole SOAP thing. X and 3, whatever's cubed, just the first power, squared. 3 squared is 9. Multiplied together, same, opposite, always positive. That's the whole, right? So the graph is behaving like this graph, other than where the hole is. So to remove the discontinuity, we would just redefine the graph as the parabola. Okay? That's us fixing the hole. That's us removing the discontinuity. Here's another problem, A and B. So f of x are both continuous and differentiable. So there's two unknowns. You need two conditions, but they've mentioned two restrictions. Continuous. So continuous is where the functions are equal. The y values are equal, because then that means there's no jump. And so what we do usually is just plug 2 in to both of these. That point right there is usually what we're interested in. So it's going to be 4a plus 2b. And this one's going to be 12 minus 9 is 3. And then we set them equal to each other. We say, well, they got to be equal to each other if it's going to be continuous. So that's one equation relating our two unknowns. Differentiability is when the slopes are equal, the derivatives are equal. So what I usually do is I take a piecewise derivative, say, okay, well, 2ax. Now remember, a and b are just numbers, plus b for x is less than 2. And this one's going to be 6. So I write a piecewise derivative, and then I plug 2 into it to see what the slopes are going to be on either side. Now, we're not trying to see if it's differentiable. We're trying to force it to be differentiable. So that's going to be 4a plus b equals 6. So 4a plus b equals 6. So now we have a system of equations that we can use to find the two unknowns. We have two separate equations to help us find two unknowns. So you could use substitution. In this special case, elimination works really well. Elimination is when you have two equations. They're kind of like the same types of equations, linear, whatever, and you could add or subtract one from the other, or multiples of one from the other. So if I subtract this second equation from this, I eliminate one of the variables. That's what I call elimination. All right, and then what I can do, and that's actually one of my answers. Then what I can do is plug this back into either of those equations to find A. Now, whichever one seems easier. They're both about the same, but I'm going to just plug it into the second one. So that's like a substitution step, and A equals 9/4. So linearization is when a differentiable function appears to look like a line if you zoom in enough. So if it's not differentiable, then it's not going to look like a line. And so any curve, you zoom in enough on your calculator, is going to look like a straight line, unless there's some discontinuity there. So like, for instance, if you zoom in here, yes, it will look like a line. If you zoom in here, yes, it's going to look like a line. If you zoom in here at this cusp, then no, you're going to still see a corner. It's not going to look like a line. So that's where differentiable functions appear linear if you zoom in closely. Otherwise, they don't look linear if they're not differentiable. So that's it. Here's your assignment. Try it. Check the odds in the back of the book. And we'll talk about what questions you have.